The next example that I'm going to work out says, after getting a steaming cup of coffee, Lopez decides that the 0.6 kilogram coffee, made mostly of water, is way too hot at 90 degrees Celsius. She decides to add ice to her coffee. If the final temperature of the coffee is 80 degrees Celsius, how much ice was added? Assume that the ice is at 0 degrees Celsius. So once again, what you're going to do is you're going to start by asking yourself who is gaining the heat and who is losing the heat. Because heat lost plus heat gained is going to equal to 0. So in this particular example, the piece that's going to gain the heat is going to be the ice. And the one that's going to lose the heat is going to be the coffee. Once you've established who's gaining and who's losing, you need to ask yourself, will any of these undergo a phase change? In the case of the ice is at 0 degrees, and it's going to, when said and done, the final temperature of the coffee ice mixture is going to be 80 degrees. So the ice is going to undergo a phase change. In order to account for that energy, I'm going to go ahead and write in mass times the latent heat of fusion for that ice to undergo the phase change. After the ice undergoes the phase change, the next thing that happens is that it turns into liquid water and is in equilibrium with the coffee at 80 degrees. So not only did the ice undergo a phase change, but it also undergoes a temperature change. You probably won't see the liquid water from this ice. It'll probably be dissolved into the coffee, but trust me when I say that the ice, once it becomes a liquid, does not stay liquid at 0 degrees. The liquid itself heats up to 80. Next thing that you ask yourself is, does the coffee undergo a phase change? If we're going from 90 degrees to 80 degrees and it's mostly water, then there is no phase change that's happening. So in the case of coffee, this coffee will only be a temperature change. Now what I'm going to do may help to keep things in order, because if you look at this formula, you've got lots of variables that get mixed around. I'm going to put this in brackets. It is not required, it just helps me remember that all of this data right here is strictly for the ice, and all of the data over here is only for the coffee. The next thing that you do is start plugging in your numbers and values. Okay, so we've got M is the mass of the ice, and that is what we're looking for when they're asking us how much was added. So I'm just going to go ahead and leave that as an M. That is my variable. So mass times the latent heat of fusion for water, which is 3.35 times 10 to the 5th. And if you don't know where I'm getting this number from, it is available on your formula sheet. It is also available on your the chart that I gave you with all the specific values. But if you look at your formula sheet at the very bottom, you've got some values here that we use for thermodynamics. There is the specific heat of water, ice, and steam, and there is our latent heat of fusion for water and steam. So this is where I got that number from. Going back to our problem, we've got mass times the latent heat of fusion for water, plus, once again, the mass of the ice, which is what we're looking for, okay, multiplied by the specific heat. Now, here's where it could get a little tricky. Once we've put in this energy, we have changed the ice into liquid water. So when we are calculating this temperature change is of the liquid water, not ice. We've already changed it by adding in this energy. It is now liquid, so the specific heat I'm going to use is that of liquid water, which is 4187. Okay, there's that specific heat multiplied by my temperature change. The initial temperature of the ice was 0. The final temperature is going to be 80. And all of this data right here comes from this bracket right here. All I've done is take this part of my equation and plug in the numbers where they belong. The next piece over here at the end of this equation is the energy that is lost by the coffee. So the mass of the coffee in our problem was 0.6. The specific heat, since it's mostly water, will be 4187. My final temperature of the coffee is 80 degrees. The initial temperature of the coffee was 90. So this is this equation plugged in with all the numbers that I have been given. And so what I'm going to do is, first thing I'm going to do is I'm going to start simplifying. I'm going to multiply these numbers together, and I'm going to multiply these numbers together. And I'm going to leave my variables, for the moment, I'm going to leave them separated. So 0 equals 3.35 e to the 5th m plus 334,960 m plus, I got this number by multiplying these two together and then distributing to the m. Now I'm going to go ahead and solve for this part right here. This I can just type straight into a calculator. And I get negative 25,122. All right, now since I've simplified all of this, I'm going to go ahead and combine my like terms. Zero equals 669960 m minus 25,122. I'm going to add 25,122 to both sides so that I isolate this variable m. Whatever I do to one side of the equal sign, I do to the other. And to solve for m, I'm going to divide to cancel out that multiplication that's going on here. And whatever I do to one side, I do to the other. And so the mass of my ice is 0.04 kilograms. And that's it.